Okay, hi now. Welcome everyone. We are in the new session of the seminar Diálogos entre Matemáticas y Cultura. Today we are present to Rinus Roelofs. He is a Dutch mathematician and a sculptor. He is graduate from the Escher Academy of Art in the specialty of sculpture and is mathematician on University of Schnell. He is fascinated with the math, in particular with the math sculpture, has allowed him create a spectacular sculpture made with matters such as paper, metal, and acrylic. Today, he will give us a talk entitled Art about Mathematics. Thank you, Rinus, to be here.
Yeah, okay. Yeah, well, I'm an artist in the first stage, so not a mathematician, but an artist. And I like mathematics very much. I think mathematics is very important, especially for sculpture. And I just want to show some examples of things I'm working on. And well, I will put my camera a little bit. So one of the first things I was working on was division of regular polyhedra. What you see here is a cube, and it's divided in 3 equal pieces. Well, when you look at this problem as a mathematician, it isn't really a problem to divide a cube in 3 equal pieces. But as an artist, you try to find new solutions. So this one, in the first stage, so not a mathematician, but an artist, I can this one take it apart, and well, you see 3 equal pieces, and in total it's the cube, but you can put the pieces together in such a way that the third piece doesn't fit in. So there are a few and when you have it in this way, you can put the third piece in. And so now this problem of dividing a cube is solved in a more artistic way than in a mathematical way. I think it's more interesting. And well, when I had this one, I thought, well, let's challenge, let's make it a little bit more difficult. Just divide a cube in 2 equal pieces, and again try to find a cube divided, which is interested in the way it's divided. So what you see here is a cube, but now divided in 2 equal pieces. And interesting about this one is that you see, when you look, you see 4 different levels of division, but it's still only 2 pieces. Well, how it's done? Well, I can just take it apart, and you see we got 2 nice equal pieces, and each of them is half a cube. So this kind of problems interested me. How can you divide those simple mathematical shapes in a very beautiful way? Like the cube. Another shape I did was the Tetrahedron. Also this one, I divided in 2 equal pieces, and again, the decoration on the sides of the Tetrahedron is equal on each of the sides. So this one, when you want to divide it, you just have to take it like this, and well, comes together really nice. Two equal pieces and together forming the tetrahedron. It's some kind of organic shape what you get, and that's all because you took a very nice cutting plane, and that cutting plane has the shape of an helix. So when you talk about a helix, you have an axis that goes from this point to this point, and around that axis the piece can turn and come out. Well, those helical paths are interesting as such, and well, I try to make more things with it. And what you see here is a surface in which you can see a lot of holes, and all those holes has a helical shape. So it goes from the top to the bottom via a helix, and in a very special way, because you see a lot of helices, and some of them are right turning like this, and the next one is left turning. So it's turning clockwise or anti-clockwise, and it's divided nicely on the pattern. These are interesting shapes because this now is one single surface, and because of those helical holes. And what you get is a surface that is very interesting when you look from the side. It gives a total different view from the top or from the side. And when you now look at the space in between the layers, you can see that those the place in between the layers has also a certain shape. And when you study this object very closely, you can see that the shape of the space in between the layers is in fact the same as the thing itself. And well, that means that you can add a layer in between the empty space, like what you see here. So two equal pieces entwined completely. You cannot take them apart. It fits exactly, and that's because of the shape of the surface. It can be shown a little bit better with this example. So again here, you see the helical holes. And now you can very well see that the shape in between the layers has exactly the same shape as the thing itself. But in this case, it means that I can just split the object into two. And also these are completely entwined. So you cannot take one of the parts away. They are entwined and form together this nice shape. Those helical shapes can also be used for bigger objects like this one. So now again, based on one of the polyhedra, we know with shapes in around a pentagon like here, and around a triangle like here. Again, this is one single surface, so it's one polyhedron with several layers, and in fact you can extend it with more layers if you want, but it still is one single surface. So I think this is a very nice result of applying a helical shape on one of the polyhedra. There's one thing that I like to point out a little bit more, and that's the fact that I'm a fan of Escher. Well, I think Escher is world famous, and a lot of people like him. But I like to study all the things he did, and I was able to go to all his sketchbooks one day, and I went on working on one of his tiling drawings, the tiling of the lizards, and I decided to make a cut in it, and I divided this drawing of Escher into 3 parts like this, and now we can just flip over the parts like this. And it fits exactly. So we can put the piece together again. And the surprise is now that the lizards are gone, and we reached another drawing of Escher, the Chinese man. And we can see that the lizards are just gone, and we just have a new drawing of Escher. So those 2 drawings of Escher could be combined in this simple kind of puzzle. Another thing of Escher was this grid that he has drawn in a few of his prints. This is a grid made with in architecture with metal bars. You can see it very often in Italy in all kinds of buildings, and then those bars are are composed in such a way that you can just slide all the pieces out, and that's to make it easy to construct the complete pattern. But Escher, always looking for interesting solutions, made this solution for himself, and this is a solution in which the parts couldn't shift. You cannot shift all the bars out. It's just a composition of Escher in which all the bars are completely linked. So this is a very nice way to make shifting patterns with those bars in which one of the bars go through the other ones. And this inspired me to also use polyhedra with this kind of grids. And what you then get, my camera is, okay. So you see the same bars again, but now I can transform this because the bars can be slid over each other. And what you see is that this is in fact a combination of the cube, as you see it is here. You can see there's a cube, and it goes to the octahedron when you slide it together. So a very nice system to combine again two things into one object, in this case the octahedron and the cube, thanks to Escher's system of grids. There's just one more object I made with this, and this one. Here you see the triangles. In fact, it's the icosahedron, but again, you can just slide it. So that's those two. Well, when we talk about Escher, Escher was the one who brought some new ideas of presenting a difficult polyhedra like this one. In this case, you see a polyhedron which is composed by 5-pointed stars, but what you see is only triangles. It's hard to understand this kind of polyhedra if you don't have the right way to show it. And well, actually came with the idea to cut out some of the pieces. So now you can really see that it's not just simple triangles, but the triangles over here are just connected, and you can see it because there are holes in the faces. So you can look through the complete object, and the object is now completely readable. You can understand what's happening. So that's a contribution of Escher to presenting polyhedra, and this was very useful. I like to show a few more things you can do with this technique. Again, here, what you see is this face, which is a pentagon. You see only parts of this pentagon, but by cutting away some of the pieces, you can now see that these parts all belong together to one pentagon. So just leaving away parts of the faces makes it very clear to understand what kind of polyhedron this is. So also for this one, this is very difficult to understand if you don't know what you're really looking at, because you only see triangle faces, but in fact this one is built with hexagons, which are yellow, and triangles, which are gray. And at the moment you just cut away some of the parts, you can really see that that this one is really a hexagon and not a triangle. So it helps very much to just take away some of the parts, and then we can get a more clear understanding of the polyhedron. Well, in fact, we have to go back to in history to understand this problem a little bit more. This was the way Leonardo da Vinci has drawn the tetrahedron. So as just a solid with just triangular faces, and next to that, he came with the idea to draw it in this way. So also here again, when you can look through the object, you can see the back side and the front side at the same time. This is very understandable. And Leonardo da Vinci did this as illustrations for a book, a mathematical book by Luca Pacioli. And in that book, they came with some more ideas about polyhedra. And one of the ideas, they called it elevation, was that they put small pyramids on top of each of the faces of a polyhedron. So in this case, when you've got a tetrahedron, there are 4 triangular faces. So in fact, you need 4 of those extra pyramids to make a complete elevation of the object. On each of the faces, we get such an extra pyramid. And to construct these objects, I came with the idea to replace the tetrahedron by this combination of 3 legs. So it's in fact the extra pyramid that we need on each of the faces, but I replaced it by those 3 legs to make it constructible. Well, what do I mean by that? Suppose I've got those 4 shapes. So each same shape is a triangle together with 3 of those legs. And now I can combine those shapes to form the tetrahedron with the extra pyramids on top of the faces. So the elevated tetrahedron. I therefore have to combine the triangles in this way. So you see the tetrahedron is getting spaced inside, and I need the last the final part to just close the complete tetrahedron, and now I can start combining the extra parts in this way. And when I do that with all 4, like this, I create, in fact, the elevated tetrahedron as described by Leonardo da Vinci. And well, I end up with this nice, simple object, which can be made well as part of a workshop if you want. So we can do this kind of exercises with children. So we start with those simple shapes, and we can explain a lot about the tetrahedron, but also about the elevation that it was introduced by Leonardo da Vinci together with Pacioli. This part that we have now can be used for other things as well. So this was the drawing of Da Vinci for the octahedron. And when you add a pyramid on top of all the faces, you end up with this object. So this is the elevation of the octahedron. And again, when I construct the total object using those pieces I have here, I can create the octahedron with the elevations, so with the extra pyramids on the top of each of the faces. And another example is, of course, the icosahedron. So here the two versions of the drawings of Leonardo da Vinci, and well, he went on with his model to make the elevation. So on top of each of the faces, you get a triangular pyramid. And when you want to make a model, you can again use those basic shapes, and you get this nice object. So this is what I developed to make it to use for workshops. When you've got this design of the elevated icosahedron, you can think about variations, and well, just to show you a few, I brought this one. So in fact, the pieces are comparable with the piece in this one. So every piece in this shape has a triangle and 3 legs going to each of the sides, and they are used to make the complete construction. It works very well, and well, there's another variation. And here you can see the icosahedron in the middle very well, and it's some kind of network going around the icosahedron, which gives you the elevations. The elevations now form some kind of second skin around the icosahedron. So yeah, 2 objects in the same thing. There was one other thing that I want to show you about this design. If you look at these parts, so the triangle with the 3 legs, there are a few other ways to use those objects, and one of them is the use of the double shape. So instead of just one triangle, I now combine the 2 triangles into one. And when I start constructing my icosahedron with these double pieces, then the final object looks like this. So at the outside, we can recognize the icosahedron, but now also in the inside, we get the construction of those triangular. I hope you can see it. So it's just an extra step in building models, which make it more interesting, I think. When I was playing with variations of the elements to build a model of the elevation version of the tetrahedron, I came around this possibility. This part looks very similar to the part I started with in this one, but the small difference gives a quite big difference at the end. So let's fold the model with the new shapes. So again here I will need 4 pieces to build the tetrahedron or the elevation of the tetrahedron. And again, I combine the base in such a way that the legs will come on the at the outside, and we see the triangles for the tetrahedron at the inside. So again, we add the third shape, and we already see the tetrahedron inside, and I can close the tetrahedron and start combining. Oh. Sorry, I took the wrong parts, but I've here the finalized object. And what you see is, again, we've made an elevation of the tetrahedron, but the outside shape is now definitely a cube. And we have to look at this object very well to see the tetrahedron again. But the tetrahedron fits exactly what you can see here nicely into the cube. So by lowering the point where the 3 pieces, the 3 legs connect, I lower it a little bit. I create a 3-sided pyramid, which has exactly the right height to get this part of a cube. And now you can use this model to explain the combination of the relation between the tetrahedron and the cube. I think this is a very nice example of making a very simple model with which you can explain very much the things of the tetrahedron and the cube. There are much more combinations you can now make with using the elevations, the elevation idea of Da Vinci. What I've got here is a cube, and the first step, the Da Vinci step, is the elevation of the cube. And now again, when I lower the points, the top points of the elevations a little bit, I can make this model so that we get faces like rhombs over here. So now we've got the 12-face rhomb at the outside of this object, and you can now nicely see the cube in the middle. So a combination between the 12-faced object. Well, it's not a dodecahedron, but it's a dodecahedron with rhombs, and the cube in the middle. So starting from the cube via the elevation of Da Vinci, we now end up with this nice object, which is again a combination of two polyhedra. There's something else we can say about the elevation of the cube. Pacioli and Da Vinci were also always talking about an elevation as an extra. So you have the elevation, but inside there's also always still the cube, because it's the cube plus all those pyramids. And if you think about the cube inside, you can say that well, there are two layers of the whole object, and I transformed the complete combination of the cube and the elevations into this object, in which you can really see that there are two layers of the object: the cubical faces at the inside, and well, the rounded off elevations, the extra pyramids at the outside. It comes out as a really interesting object, and that's because when you look at it in a certain way, you see the knot shape at the top. So just follow this line, and you will see the knot shape. So that's interesting that with a number of knot shapes, you build the skeleton of a really new kind of objects, double-layered objects, which are still in fact based on the elevation of Da Vinci. I brought one more object in this sense. So again, I like to start off with Leonardo's drawings. So he made the drawing of the cube octahedron. The 8 triangular faces of the octahedron combined with the 6 square faces of the cube. Again, you can see that if you draw it like this, it's not very clear, but if you draw it like this, you can look through the object and see all the faces, which makes it very clear. So Leonardo started again with making the elevation object. So it's a second skin around this one, and there's this one. And if you again make a round-off version of the two objects inside, you end up with this one. It's a little bit different from the other one, because now we end up with two entwined objects. It's not one single object, but it's two objects. So that's a big difference between the cube, what we had here, and the cube the cube octahedron, which we have here. Can we explain this? Well, when we look at the cube, we see that there are three faces come together at one vertex point, and if the cube octahedron, there are four faces coming together, and that's what you see here. This was my vertex point of the cube octahedron, and well, in the case of the cube, it turned out to give us a knot figure, but now we've got four faces coming together, and so now it's two ellipsoid shapes entwined instead of a knot. And so in the print, it's two separate objects. So we really need an odd number of faces coming together to get those knotted faces. And one of the objects that can be used then is the snub cube. Well, Leonardo da Vinci didn't make a drawing of this one. He apparently didn't discover this one at that moment. But well, with the technique of da Vinci, we can make this model and even think about the elevation of that object. And finally, we end up with this object. And in this case, we see the knot figure at this point. And because there were five faces coming together at each of the vertex points, it's now a five-folded knot. Well, da Vinci did a lot about drawings, making drawings of polyhedra in such a way that it could be better understand what kind of object it was. You could, by the way that he made the drawings of polyhedron, you could really look through the object and understand more of what's the case. But some decades later, there came another artist with a very good idea of making the polyhedra understandable, and it was Albrecht Dürer. Albrecht Dürer came with the idea of making plans of polyhedra. So till that time, and we're talking about 1500s, around 1500, all models were made in wood. And the drawings of Leonardo da Vinci were made by looking at wooden models, or just thinking about how it would it be, and then make a drawing, so just by head. At that time, people didn't make paper models. Albrecht Dürer was the first one who came with the idea to use paper and to first draw a plan of it. So let's take this one. So what you see here is a plan for a cube. So you take a piece of paper and you cut out this shape, and then you can fold, and you've got a nice model of a cube. Very easy. But someone had to come up with the idea, and that happened to be Albrecht Dürer. He made He has written a book in which he explained all this, those kind of plans for polyhedra. And so this was his idea of making a dodecahedron. You just make this on paper, you cut it out, and you can fold it, and at this way, making very easy a model of a dodecahedron, which was more easy than making a wooden model. This took yeah. Uh, this was very difficult to make. You had to calculate all the angles, and in this case, you just fold it, and you get your model. So the most simple polyhedron is this tetrahedron, and this was Albrecht Dürer's idea of making a tetrahedron. And when we try to apply this technique of making plans on the objects we've seen just before, so with the double layers, the objects that I made from the elevations of the polyhedron. So based on the elevations of Leonardo da Vinci, I made objects, and now the question was: can we use Albrecht Dürer's technique to make the models in a more easy way? Well, the first object that I tried was this tetrahedron, which was a double layered, as you can see. So in this way, you see the double layered tetrahedron. And when you want to make a plan of this object to make more easy, to make it more easy to make the model, I came up with this one. And when you look good, well, in fact, what I did is just double our Dürer's model to make the double layered tetrahedron. Just simple like that. You want to make a double layered tetrahedron, so you double the plan of the tetrahedron. And really it works. So we can fold this together to make this double layered object. It takes some time because you have to study how to fold this plan to get this, well, in fact, a knotted object. Because also here, just what we've seen by the double cube, when you would really follow the line around this point, you will see the knot again. So you have to knot this plan really to make the final object. It's nice that you can do it in one, but I had another idea, and that was to do it in two. So why not make two parts of the plan like this, so you can recognize the plan. And when you now look at the model, you see that if you follow one color, that a face at the outside is connected to a face of the inside, and so on. So it switches from outside to inside. So to make the final model, I have to really weave these parts together like this. So now both parts are woven, and you then can begin and you see that the object is built in this way. So by starting with two plans, weave them together just like this, and then after weaving, folding, we get a nice double-layered object. It's nice to see that there are two different plans for a tetrahedron. So Albrecht Dürer chose this one to have in his book, but we can also use the triangular plan for the tetrahedron, and then when you weave, we start with two plans, and again we have to weave them together. But we can now do it in this way, that we just lay them on top of each other, and now you just have to rotate, and you get the situation that an outside triangle is connected to an inside at all three sides, and the final object is again a double-layered tetrahedron. Well, this technique is very inspiring because we can apply it on almost every polyhedron, and what you see here is the cube, and well, again in a few steps, the first idea is to make just one plan and try to build the double cube, starting with one plan, and try to fold it in such a way that you get this as a result. It is possible, and well, I can show you the plan, and this is the plan that you need. Quite a long strip, and it took some concentration to fold it in the right way to get this. So also here, the technique of using two layers of two parts for the plan, and then weave them together is more fruitful. So what you see here is two of Albrecht Dürer's designs for the folding a cube. But now again, we can just put them on top of each other and weave them. like this. So again, you see here the faces going outside and inside, and when you fold the complete model, you end up with the nice double-layered cube. This was Dürer's pen I used here, and well, of course, you can take any of the what we now know 11 different plans for a cube. In some way, I have my favorite plans for the cube, and that's not this one, but that's more a plan like of this type. Nice from this kind of plan is that it's just one strip of faces that you get to have as a plan for the cube, and it's also nice that you need two exactly equal copies of those plans. Well, to have the outside and the inside in a good situation, I just have to rotate this before I just going to weave the face, the parts together, and then you see the weaving is a very smooth process. So in this way, we've got the outside part above the inside part, and then when you fold, you get the nice cube again. So the tetrahedron and then the cube are relative simple objects to make with this technique, and it becomes more interesting maybe if you take a difficult object. And well, let's take a look at the dodecahedron. So also here you see the double-layered object, the dodecahedron, and this is what you need if you want to make it in one step, in one plan. Quite complicated, but you can do it. This one is built with this plan, so that's a possibility. But it becomes more interesting if you can use dual plans. And then so this is exactly based on Albrecht Dürer's plans for the dodecahedron, and then it's more understandable what you are doing, and it works like weaving, folding, and that's a very nice way of doing it. And so almost any polyhedron can be made in this way. So just weave and then fold, and then you get this double layered objects. There's one thing you can remark on this one, because we started with drawings of Da Vinci in which the double layered was formed by just a small pyramid. It was attractive in that sense that you had a pyramid on top of each of the faces. And the idea was, can we make such objects by, again, using normal plans that you could cut out of paper and then fold it into this kind of objects. It took some study, but it also can be done with the dual plan approach. So this is a plan of cube, and here the same. You need two of them, and in this case, you can recognize three squares, and here 3 parts that come together as a pyramid. So again, in just one simple flat plan, we can make both the inside squares and the outside pyramids. And after weaving, so before folding to the final shape, you have this version of the interwoven 2 plans. So now the steps are: first fold, but fold only the parts which has to be the pyramids, then weave, and then fold again. And you get objects like this. We already have seen that it helps very well if you take away parts of the faces, so you can now really have a look inside. And so with the use of just 2 plans, we can make a model of this in which we can see the outside and the inside cube as the combination in this object. I would like to show you one.
Sorry, Rinus. You have only 3 more minutes, please.
Yeah. Okay. Yeah. Yeah. When we do this approach with the icosahedron, then this is my plan of one of the parts of the icosahedron. So also for this one, I first have to start folding, and then you see that I've started to fold some pyramids over here, and after I folded all the pyramids, I can start weaving and then folding to the final object. So you really end up with this nice object. Well, there's much more to say, but yeah, I took already an hour, I see. What I want to remark now is that when you look at Dürer's method of making models, it's very powerful. You can use plans in many different ways, but essential of using plans is that you don't have to bother anymore about the angle. You don't have to calculate the angles. Well, it's what you have to do with the Roelofs model. You have to know really the angle between the faces. When you make a paper model, you just fold it that they until they reach, and you can glue it together, and you have your model. So in fact, what Dürer did is taking the whole thing of making models out of mathematics, and it becomes now available for almost everyone, and just built with paper. So I think Albrecht Dürer made a very big step with this simple idea, and most of the people don't recognize this as a main point in history, and that's what I want to focus on. So thank you. That's what I want to add for now.
Okay, thank you very much. It was a really wonderful talk. We learned so much. I will present some comments that we have in the Facebook. Remember to all the audience that we have here in the room to stay after after these questions to keep talking. So we have a comment from Mike Acerra. He asked you, from your point of view, what comes first, the beauty or the math? Is the math an afterthought of the beautiful forms you make?
And I would say that I used the beauty to make math understandable. So yes, beauty is very important, but what I want to do with beauty is to make math understandable. So I think it's important that more people really understand math.
Okay, well, we thank you very much. There are a lot of congratulations on the Facebook channel where they say that you have a beautiful work and they will be watching the video once and once again. So for all the audience, remember that in 2 weeks we have the next mathematical and culture dialogues session with Albina Arroyo that we will be talking about matemáticas visibles. And I will say this in Spanish also. So, muchas gracias a todos los que nos están siguiendo por el Facebook. Agradecemos mucho a Rinus por su maravillosa plática. Y recuerden que en 2 semanas tendremos la participación de Albina Arroyo con su exposición de matemáticas visibles. Muchas gracias y hasta la próxima.